In this video, I'll be talking about one of the most powerful statistical techniques called the Generalized Linear Model, and I'll be showing you how to conduct the analysis in SPSS. My name is Titocan, and this is Titocan Mark Solutions, a YouTube channel for improving the knowledge of how to do things. So stay with me on this channel as I walk you through the step-by-step approach from understanding the concept to running a practical demonstration in SPSS. Generalized linear model is an extension of linear regression that allows for different types of response variables, including continuous, binary, count, and categorical outcomes. It accommodates non-normal distributions such as binomial distributions, Poisson distributions, and gamma distributions. That is, generalized linear model builds upon the foundation of linear regression but relaxes the assumption that the response variable, which is the dependent variable, must be normally distributed and have a linear relationship with the predictors. However, there are a few assumptions that qualifies your data to be used for generalized linear model. 1. The predictors should contain both categorical and continuous variables. 2. Your data should have independent of observations. That is, each case should be independent of the others. 3. Relationship between predictors and outcome should match the choosing link function. That is, appropriate choice of correct link function should be made. You will understand this better when we conduct the analysis. 4. The residuals should follow an appropriate probability distribution, such as normal distribution, Poisson distribution, or binomial distribution. And 5. There should be no severe multicollinearity. That is, the independent variables should not be highly correlated. Now, let's go into SPSS to see the data I'll be using for this demonstration. This is the dataset, and it consists of 20 randomly selected employees across different departments in TMS company. Each employee provided information about their gender, years of work experience, and job satisfaction score, which is measured on a scale of 1 to 10, with 1 being very dissatisfied and 10 being highly satisfied. The idea is to examine how gender and years of work experience influence job satisfaction among employees. This data information will help the human resources managers and the company executives understand whether demographic factors significantly impact job satisfaction levels, which can inform better workplace policies and employee engagement strategies. As you can see, the independent variable consists of categorical and continuous data and therefore is suitable for generalized linear model analysis because it allows the analysis of both categorical and continuous predictors simultaneously. As you can see, the dependent variable, which is job satisfaction score, is a continuous variable and fits the normal distribution assumption. The independent variables, which include the gender and years of work experience, are categorical nominal variable and a continuous scale variable respectively. These data settings makes it appropriate for generalized linear model analysis. In this case, the research question that the human resources manager may be asking will be, does gender and years of work experience significantly influence job satisfaction among employees? The answer to this question lies in the results that will be produced at the end of the practical demonstration in SPSS. For now, the research hypothesis will be stated as follows. The null hypothesis states that gender and years of work experience have no significant effect on job satisfaction, while the alternative hypothesis states that at least one of the predictors significantly influences job satisfaction. So our job is to find sufficient evidence to reject or accept the null hypothesis. Now, let's perform the generalized linear model analysis. Go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Generalized Linear Model. And from the drop-down options, click on Generalized Linear Model to open the dialog box. As you can see, there are several tabs in this dialog box, and each tab has several features. In this demonstration, I will give you a step-by-step guide. The first tab here is the type of model. Now, since the generalized linear model analysis, which we are dealing with here, is an extension of linear regression, then the model type must be linear. In this tab, the radio button for linear has been selected by default under the scale response, but ensure that the choice for distribution is normal and the choice for link function is identity function for the linear model. This is to ensure that the relationship between predictors and outcome match the choosing link function as required by the assumption number 3 in this video. The next tab is the response tab. Here, your variables are in the box on the left. Now, click on the job satisfaction score, which is the dependent variable, and then click on this transfer arrow key to move it to the dependent variable box. There is nothing more for you to do in this page. So, move to the next tab. The next tab is the predictors tab. The predictors tab allows you to specify the factors and covariates used to build model effect and to specify an optional offset. On this predictors tab, your variables are in the box on the left. So select gender and click on this arrow key to move it to the factors box as a categorical predictor. Then select the variable years of work experience and click on this transfer arrow key to move it to the covariates box as a continuous predictor. Now, click on the options button to open the options dialog box. This is where you can fix missing data or missing value in your dataset. The default selections here are the best options for you, whether there are missing values in your dataset or not. So just click cancel to close this dialog box. Now, open the model tab. In this tab, select all the variables in the factors and covariate box on the left and transfer them to the model box at the right. Ensure that the build terms type is mail effect. Since we are not sure the data may pass through the origin, then ensure that the box for include intercept for model is checked as it is done by default here. But if you can assume the data passes through the origin, you can exclude the intercept and uncheck the box. But for this demonstration, I will leave it checked. The next tab is estimation tab. In this page, leave every default choice unchanged. There is nothing more for us to do here. So let's move to the next tab. The next tab is statistics tab. Please ensure that the default selection for analysis type is type 3 and the confidence interval level is 95%. Also, ensure that the selected chi-square statistics for type 3 is wild and the confidence interval type is wild also. This selection measures how much a predictor contributes to explaining the dependent variable. In the print section, the basic required results output options have been chosen for us. But if you like to add more, you can choose more options depending on your research objectives. But for this demonstration, I will restrict myself to the few basic ones already selected by default, and the result will be produced as tables in the output window. In the tab for estimated marginal means, our factor in this model is gender, as you can see in the box on the left. If you wish to determine the marginal means of the gender, you can therefore transfer the gender as a variable from the factor and interactions box on the left to the display means for box on the right. And under the contrast column, click on the drop-down button and select the appropriate options you require for the marginal means, and then check the box for display overall estimated means. But since gender is just male and female, I don't intend to determine the estimated marginal means of the factors in the model. So I will undo everything that I have done on this tab. The Save tab and Export tab contain information that are entirely optional to you. And so, I do not consider the tabs as specifically relevant to the subject of description in this demonstration. So, like this, we have successfully completed the configuration procedure in SPSS to perform the Generalized Linear Model GLM. Now, go ahead and click OK for the SPSS system to process the configuration and produce the modeled output statistics in the output window. As you can see, the results have been produced in the output window. Now, I will discuss or interpret the table one after another. The first table here is the model information table. This table displays the name of the dependent variable and other functions used in the model. As you can see, the dependent variable is the job satisfaction score. The probability distribution used is normal distribution, and the link function used is identity. This table confirms that SPSS has run generalized linear model with the normal distribution and identity link function. The next table is the case processing summary table. This table displays the number of participants or cases and the percentage of cases included and excluded from the analysis. As you can see, the number included is a total of 20, accounting for 100% inclusion, indicating that there was no case excluded in the model. The next table is a categorical variable information. This table displays information about the variable used as a factor in the model. As you can recall, the variable we used as factor was gender, a categorical variable labeled as 1 for male and 2 for female. As you can see in this table, the number of male factors is 10, accounting for 50% inclusion in the model, and the number of female factor is also 10, accounting for 50% inclusion in the model as well. Suffice to me that a total of 20 cases, accounting for 100% data, were included in running the model. The next table is a continuous variable information. This table displays the descriptive statistics information about the variables used as dependent variable and covariate variable in the model respectively. In the model, job satisfaction score was used as the dependent variable, while years of work experience was used as a covariate variable. They are both scale variables containing continuous data, hence the descriptive statistics information in this table. As you can see in this table, there are 20 cases for job satisfaction score. The minimum is 4 and the maximum is 9, meaning that no employee in the TMS company has an extremely low or extremely high job satisfaction. The average job satisfaction score is 6.95, suggesting a moderately high level of job satisfaction. The standard deviation is 1.538, indicating relatively low variability in job satisfaction, as most job satisfaction scores are clustered around the mean. This means that the job satisfaction scores are relatively consistent across employees with no extreme outliers. On the other hand, there are 20 cases for years of work experience. The minimum is 3 and the maximum is 30, indicating the least experienced employee has put in 3 years of work experience, while the most experienced employee has put in 30 years of work experience. The average years of work experience is 14.70, showing that employees have moderate work experience. The standard deviation is 7.781, indicating significant variability in work experience across the employees. This means that some have only a few years of work experience, while others have decades of work experience. Now, the next table is goodness of fit. This table provides important statistics to assess how well the model fits the observed data. The key statistics to consider in this table are deviance and Pearson's chi-square. And the associated important column to consider in this table is the last column, which is the quotient between value and degrees of freedom. So the result in this column is obtained by dividing the results in the value column by the degrees of freedom. So if value over df is equal to 1, it means an ideal model fit, suggesting a well-fitting model. If value over df is greater than 1, it indicates over dispersion, meaning there is more variability than expected by the model. And if value over df is less than 1, it indicates under dispersion, meaning there is less variability than expected. As you can see in this table, the quotient for deviance is 1.661 and the quotient for Pearson's chi-square is also 1.661, and they are both greater than 1. This means that the model fits reasonably well but has some mild over dispersion because there is higher variability in the dependent variable than the model assumes. But don't forget that the data I used for this demonstration was fictitiously generated, so your real-time data may provide a better model fit. However, while this model explains job satisfaction fairly well, some unexplained variability remains. If you have a similar case with your dataset, you may consider refining the model by adding predictors, checking residuals, or adjusting distribution choice. Unfortunately, these options are beyond the scope of our objectives in this video. Now, the next table is Omnibus Test Table. This table displays results that can be used to evaluate whether the overall model significantly improves the prediction of the dependent variable compared to a baseline model such as the intercept-only model. To determine any significance, you will have to consider the p-value designated as xig. So, If the p-value is less than 0.05, it means the model significantly improves the prediction. But if the p-value is greater than 0.05, it means the model did not significantly improve the prediction. So as you can see from this table, the p-value is 0.010, and this is less than 0.05. This indicates that the model significantly improves the prediction of job satisfaction score compared to an intercept-only model. This means that at least one of the predictors, such as gender or years of work experience, is statistically significant in explaining job satisfaction. Now, let's proceed to the table of test of model effects. This table displays results that assesses the overall significance of each predictor in the model and tests whether an independent variable as a whole has a significant effect on the dependent variable using type 3 test. Although this table is repeated in the parameter estimates table, and you might be tempted to omit discussing the results in this table and move on to the parameter estimates table. Please, I am here to guide you. Don't omit this table because there are key differences between the information provided by the test of model effect table and the parameter estimates table as far as the generalized linear model analysis is concerned. The procedure is to always check the test of model effects table first before moving on to the parameter estimates table, because the test of model effects table gives you the indication whether a predictor significantly makes contribution or not. So in this table, each row represents an independent variable such as gender and years of work experience. Now, our interest in this table is to look at the p-value results for each predictor, because by significant effect, the p-value is inversely proportional to wildcat square. So if the p-value is less than 0.05, the predictor significantly contributes to explaining variability in the dependent variable. But if p-value is greater than 0.05, the predictor does not significantly contribute to the model. So as you can see from this table, the intercept has world chi-square of 104.794 and a p-value designated as SIG of 0.000. The p-value is less than 0.05 and so is highly significant, indicating that the dependent variable, which is job satisfaction score, has meaningful variation that can be explained by the model. For gender, the world chi-square is 7.523 and the p-value is 0.006, which is also less than 0.05. The p-value is low and shows that gender has a statistically significant effect on job satisfaction, meaning that male and female employees experience different levels of job satisfaction. However, the actual impact will be known when we discuss the parameter estimates table. For years of work experience, the wildcat square is 3.869 and the p-value is 0.049. The p-value is very close to 0.05, meaning it is marginally significant, suggesting that years of work experience affect job satisfaction, but the effect is weaker compared to gender. So as you can see from this table, both gender and years of work experience significantly affect job satisfaction, with gender having a stronger effect. Years of work experience has a borderline significance, meaning further investigation is however needed to confirm the strength of its impact, and the intercept is highly significant, confirming that the model captures meaningful variation in job satisfaction. But to understand the exact impact of gender and years of work experience on job satisfaction, since there is significant effect, let's proceed to interpret the parameter estimates table to see the direction and magnitude of these effects. This table provides crucial details on the estimated effects of each independent variable on the dependent variable. This table has several information, but the most important columns to be considered in this demonstration are as follows. The coefficient designated as B, which can also be referred to as the odds ratio, shows the magnitude and direction of the relationship between each predictor and the dependent variable. The magnitude is the value of the coefficient B, while the direction is indicated by the positive or negative indices attached to the coefficient B as prefix. If the coefficient B is positive, it indicates an increase in job satisfaction, while if it is negative, it means there is a decrease in job satisfaction. The higher the coefficient B, the higher the effect or the impact. 2. The p-value, which determines the statistical significance. In this case, if the p-value is less than 0.05, the predictors have significant effect, while if the p-value is greater than 0.05, the predictors have no significant effect. So as you can see in this table, the intercept has coefficient B of 6.666, which is positive. This represents the baseline of job satisfaction score when all independent variables are at their reference values. The p-value is 0.000, meaning the intercept is highly significant, indicating the model predicts a meaningful starting value for job satisfaction. For gender equals 1, which is male gender, the coefficient B is minus 1.459, which is negative, meaning that males have 1.459 lower job satisfaction scores than females, and the p-value is 0.006, showing that this difference is statistically significant. Suffice to mean that gender has a real effect on job satisfaction. However, in this table, gender equals 2, which is female, is set to 0 because it is used as a reference category and therefore the parameter is redundant across the column. For years of work experience, the coefficient B is 0.069, which is positive, indicating that for each additional year of work experience, job satisfaction score increases by only 0.069 points. The p-value is 0.049, showing that the effect is marginally significant, indicating that the work experience has a weak but meaningful impact on job satisfaction. Generally, this result shows that gender has a stronger effect on job satisfaction than work experience. So unfortunately, we do not have sufficient evidence to accept the null hypothesis. So we will reject the null hypothesis because at least one of the predictors, which in this case is gender, significantly influences job satisfaction. This information could be useful to the human resources manager for decision making or policy changes. And that wraps up our class today on the generalized linear model in SPSS. And I hope you'll be able to replicate the procedure to run the analysis on your own dataset and interpret the results. But wait, don't stop here. If you found this tutorial helpful, click the like button, subscribe to Titocan Mark Solutions for more data-driven insights, and hit the notification bell so you never miss out on our latest tutorials. Do you have questions? Drop them in the comment section. Let's keep the learning going. And hey, if you are working on a real-world project and need guidance, let's talk, because learning never stops. Thanks for watching, and thanks for subscribing to Titocan Mark Solutions, a YouTube channel where we break down complex data analysis into simple step-by-step tutorials. But remember, data speaks, but only if you know how to listen. See you in my next video. Bye.